Okay, so now we're going to look at the last topic in AP Unit 9. That's 9-9, finding the area between two polar curves. And so basically the idea is we could have a polar curve that maybe does this, and then another one, that's amazing, isn't it? And then another one that maybe does this. And maybe we want the area in here. And so we would need to find the area of two different parts. The trick is that we have to figure out exactly, first of all, where do they intersect? That's the number one maybe headache or challenge in this, and we'll talk about that in a second. And then the other thing you need to think about is, let's suppose we specifically want this area between the XY axis in this particular graph. Well, then what you have to do is you have to say, okay, on that brown graph, what are my bounds from the beginning there at the bottom to that intersection? And so that's going to be the first area that we're going to find. And then on the black line, we're going to have to find the bounds from that intersection over to the stopping point there, which might be pi halves or it might be something else. And so then in that case, we're going to find the area of the black there that I've kind of darkened in green. So it's just you really have to keep straight which line, which curve belongs to which piece whenever you are setting these up. So let's talk about finding that intersection point. That's really the primary headache, I think. So number one, to find the area between two polar curves, you must find the points of intersection between the curves. You can find those intersection points in several ways. Maybe you're given a graph and you can just look and see. That'd be awesome. You might need to put the curves into your graphing calculator and find where they intersect. Or you might need to do it by hand by solving for theta. Let's talk about those last two ideas here for a second. So if you're going to put a graph in your graphing calculator, two different curves to find where they intersect, first of all, you want to change your mode to polar form. And then that helps you graph and lets the calculator know exactly that you're graphing polar equations. But then that changes kind of the calculation options that you have whenever you use a graphing calculator in its regular, function mode. And so there's not a second calc intersect anymore. So what you need to use is just hit the trace button and arrow left and right, so that usually to the right, because it's going to start at 0 and it's going to go up from theta equals 0. So you're going to arrow to the right until you get to the intersection. Now, this creates a few issues. First of all, you do know from your calculator, if you hit the up or down arrow, it will jump to the other curve. So one curve might be a little easier to arrow to trace around than the other one. But what happens is every time you hit that button to the right, you've got to know how far you're moving, because it's going to list it in weird decimals. So you can go to Window on your calculator, and if you've never changed it or no one else has ever changed it and you're in polar form, then usually your theta step is set at a pretty weird looking number, 0.1308996. And all that is pi 24ths. So every time you hit your right arrow when you're tracing over a polar form graph on a TI calculator, you're arrowing over pi over 24. So take 12 of those to get pi halves. So you can kind of use that fraction to figure out. And usually the answer of the intersection will be, like pi 6 or 2 pi thirds or pi thirds or pi fourths, or, one of those that's pretty familiar to us. Now you can also set your step size to be pi over 24, and then that, if it's not already that already. All right, so using graphing calculator to find where they intersect is one thing. Sometimes you might be doing a problem on a non-graphing calculator section of the test, or non-calculator. So then you just set each equation equal to each other and solve for theta. So like we have r equals cosine of theta and r equals sine theta. well, then we would just set sine of theta equal to cosine of theta and find out their points of intersection. Now, they're probably, they might intersect in more than one place, so you need to read the question and ask you so that you figure out exactly what it wants you to be graphing. Okay, I want to read a little bit more, then I'm going to do an example with you. Number 2, in cases where you need to find the area of a symmetrical region, it might be easier to find the area of just half the region and then double it. Double if half the region gives you bounds that are easier to work with. And you're going to see that with me here in just a second on the problem I'm going to do. And then finally, like last lesson, it might be necessary to remember the half angle identities for sine squared of theta and cosine squared of theta. Okay, so let's take this limicon 1 plus 2 cosine of theta. And I have it in different colors because I wanted to highlight some different things here. But let's say that we had a question that said, find the area of the outer loop of this limicon. Okay, so we know that it's 1 plus 2 cosine of theta is the whole limicon, but we want to just find the area of this outer loop, right? We don't want that inner loop. So what we need to find, that's again probably the most critical part of this, is we need to find that point, and it's actually going to be 2 points. As we work from 0 and go around, I'm showing this pink line, we're going to hit a point that starts the inner loop working. Then we're going to hit a point again that ends the inner loop and gets us back to our outer loop. So you've got to find those points. And so this would probably be a graphing calculator question, and you would graph this out, hit trace. Your trace would start over here at 0, and every time you right arrow, it would be going pi 24ths. And then what would happen is that you would find out that we first hit that at 2/3 pi, or 16/24. So in this particular problem, we have 2/3 pi, 2 pi thirds is a point of intersection. Then as you're hitting trace and you're going around the inner loop, you're going to find out that we hit again at 4 pi thirds. So if we want to find the area of the outer loop, we have to find the area from just those bounds, right? So from 0 up to 2 pi thirds, and then from 4 pi thirds up to 2 pi. Or you could do the entire limicon from 0 to 2 pi and subtract off the inner loop from 2 pi thirds to 4 pi thirds. I think that's a little bit longer, and I'll show you how the other way is a little bit shorter. So here we go. We're using the same area formula from 9-8 in AP Calculus. It's half of the function squared, and we want to go from 0 to 2 pi thirds to that first intersection, and then we'll pick it up on the other side. So another integral, a half, of 4 pi thirds. That's where we come out of that inner loop, up to 2 pi of the function squared. And so that's what you do. And we're not going to work out the numbers on this, but if it's a calculator problem, you're just going to plug the function in your calculator, make sure you square it, and then integrate it. Now, I do want to point out something that makes it a little bit easier. On the calculator, maybe not so much, but if you're doing a problem by hand, my goodness, let's just realize that this shape and a lot of our polar form shapes are symmetrical. So we can kind of just cut this down down the middle, and really just look at the top half. And so we really only have to go from 0 to the 2 pi thirds, and then just double our answer, because it's going to be the same in the bottom. So what happens then is whenever we actually go to work out the math on this, what might be an easier integral than each part would be to say, okay, I'm going to double the area of the first part from 2 pi thirds f theta squared d theta. And then that's just going to create less work for you. So there you go. Really, the calculus isn't hard. It's maybe setting it up, making sure that you find your intersection points here on part 1. That's the part you might need to practice a little bit. And then once you get that, the only other part is making sure that you recognize, okay, if we want, you know, a certain area where the two shapes overlap or whatever it asks for, just make sure that you are looking at which shape is your start from 0 to the intersection point, then which shape picks it up from there, which line. So there you go. That